All right, well, this is sort of an introductory talk to the Texas Advanced Computing Center. So I'm Niall Gaffney. I'm one of the astronomers in the room with ties to NASA because I did work on the Hubble Space Telescope for 14 years. So I've been dealing with big data when big data was measured in pounds because you carried platters around. And so, you know, I think of a lot of this as being very exciting where things have gone from humble roots to where we are today. But at the Texas Advanced Computing Center, I'll get into what we are and who we are in just a minute, but people are coming in with different data problems for us, and they come to us sort of, I think, in sort of, they have two legs of the problem, but the third one is always missing. And so you have people coming in with great data that can solve their problem, but you know, they can't do it on their own hardware, or moving data takes too long, or sharing with their comrades is too difficult. Or they have this workflow that solves their problem, but you know, my laptop catches fire halfway through these times. Or it only runs on this old PDP-11 I've got from the 1970s over here in the corner. And then the third problem that needs to be solved is that, you know, they have this problem that needs to be solved, but they really don't know, given all of the things that have been talked about here today. You know, there's this magic black box that people talk about in machine learning. Can I just drop my stuff in there and have it work? And I have people come to me all the time with that question. And the answer to that is yes, if you make the black box right. And then there's this problem of I don't know where the data are, and finding data and getting data out of data silos. And so I think we've heard some very good coverage on that from the previous talk. At the Texas Advanced Computing Center, we're located at the University of Texas at Austin, just 3 hours up the road, plus or minus traffic. There are about 160 people on staff at the Texas Advanced Computing Center. 70 of us have PhDs and everything from, I can't quite say astronomy to zoology because we don't have a zoologist on board, but it's really close to doing that. We have people we have an entire life sciences division that works largely in genomics and other aspects of studying cancer and working with folks here at MD Anderson. But we actually have a very large facility up there with a 12 megawatt data center, 2 office buildings, and really about 15 different clusters that we run for all different problems in sort of the digital realm. We give out, you know, this is a Texas style talk, so you know, you talk about billions and billions of all sorts of stuff, but we have large numbers of flops and large numbers of petabytes of data. And we really sort of support every kind of computing that's out there today. So we really do fill out the buzzword bingo on that part. But the real thing is, while we do have racks and racks of computers, we also have all these people. And that's really where I think the center comes together as being sort of this glue that tries to bring all the techniques, technologies, data, and people together to actually solve problems. We have extreme scale supercomputers. I mean, that's what we're there for. Is to give people the flops they need. If you haven't been reading the HPC news, and not everybody follows that, we recently deployed the first half of our Stampede 2 system, which now is the number 12 high-performance computer in the world. We're adding to that, and I wouldn't write it down because it hasn't been tested yet, but we hope to be back in the top 10 very soon for doing sort of HPC sort of computations. We have a cluster that we run for Texas-facing computing. It's one that is supported by all 3 major university systems here in the state and allows people to come in and do that HPC sort of work that they want to do in the Texas systems without having to go through the long queues that you get on the national systems. But sort of the interesting ones that we have for data here, Wrangler is a system I've been working on for a while, which has about, well, we like to say 0.6 petabytes or 600 terabytes of interconnected NAND flash memory. That means that we have a system basically that has unlimited IOPS. And we've been using this sort of system to do a lot of the data problems that don't fit into normal HPC systems. Small reads, small writes, analyzing web content, and I'll show a couple of those coming up. But it's a file system that really is meant for compute, and then also a large shareable file system for putting data, cataloging the data, and getting it out to the people. Maverick is sort of our current and forward-moving GPU system. That's where a lot of our machine learning is going on these days. We've got Kepler K40s and some P100s in there now, and we'll be moving on to other ones in the near future. We operate cloud sort of systems, whether you're talking about true VMs or being able to do computer science, bare metal allocation of nodes to play around with how to optimize data science problems. We have a lot of people doing that there, as well as lots and lots of tape and storage. Another interesting system that we have here, though, is our Hikari system, which is a system that was given to us by NTT and NITO, who are basically the Department of Energy in Japan. They're interested in operating this thing at a 380 volt DC in the data center. We're interested in it because it allows us to have a very secure compute environment where we're hoping to do a lot of the HIPAA and sort of ITAR and other protected data work that people need. So we're really pushing a whole bunch of systems out there to cover the different things that people need. And we're also pushing some of the boundaries around here of what it means to be a high-performance computing center. And you'll see some of this, we've already had allusions to this, that machine learning and deep learning is coming into play even in HPC to do dimensional reduction or to help constrain problems. But we're very interested in where things are going to go with this and what systems you're going to want to buy. And so we've been doing some interesting studies just to see how cost-effective and how different kinds of systems can be put together to address different problems. And so the Stampede 2 system is largely made up of the Xeon Phi Knights Landing nodes. And we are very interested to see how that compares to the GPGPU systems with P100s, which are sort of, or were as of a few weeks ago, the state of the art of the GPU world. And what we found sort of in some of the work that we've done using a system of Caffe that was optimized for the Xeon Phis is that a couple of Xeon Phi nodes are basically in the ballpark, same equivalent as a P100 node, which is sort of means that your price per flop on that, if you will, is about the same given the cost point of both of those. So we're very interested in pursuing this and seeing where this is going to go. And so we're not picking sides on this. I'm not saying blue is better than green or vice versa, but we're one of those centers that's going to go forth and sort of look into these things and explore where the new technologies are going. But we're going to continue with this Maverick system for GPGPU because not everybody is going to optimize things for the CPU. You're still going to have a lot of companies using CUDA. I mean, Google is big into TensorFlow, and TensorFlow runs best on GPUs. And so we're also interested in the technologies. So we try and put all that stuff together and then help people solve their problems, their research problems. We've heard a few other talks here about Harvey. I was actually in the middle of the South Pacific when Harvey hit and came back to a lot of rain in Austin just as things were opening back up. But got off the plane and very quickly thereafter, there was a lot of things that had to happen that were going on. And of course, we have been running simulations of the storm on our systems and done some sort of coastal inundation flooding due to storm surge. But the two things that sort of came up when we got back that were very important to get to people's hands at the Texas Task Force 1, so the people who were getting the boots on the ground really, was to get sort of both imaging data wherever we could, working with CSR to get information about what the inundation was from that point of view. But then also working with David Maidment at UT Austin, we got together, we started on a Friday afternoon, I got the call saying we need to put this together, and by Saturday morning we were up and running, taking the national weather models and trying to see if we could map that with the river systems to come up with the flooding and inundation so that people knew where that they could put the first responders in at sort of the block by block level. So I don't know how well all of this worked out completely. We still need to sort of debrief a bit on this, but we really want to move in this sort of way to get this data as well as simulation-driven, first responding, helping responders act directly when disasters like this strike. Not to just keep harping on sort of storm problems, but the other thing that we have been doing, this is, I believe, working largely with some folks at the University of Oklahoma. They want to understand how to better forecast hail. Hail is a very difficult thing to forecast from sort of the simulation point of view. What they found is if you do one of these combinations where you train the evaluations of your model data with data from previous storms in the area, you can actually extend these forecasts for where severe weather is likely to produce hail from 2 hours to 24 hours. And that's a game changer, because it's not just, pull my plants in and make sure the car is parked underneath the carport this time, but you can actually take some action to make sure that everybody is prepared for it with some real planning. We've been working on sort of a lot of image identification and in sort of the 3D brain space in this case, but also in a lot of other health related research projects. But this was George Biros who was involved with it was actually a competition where they had 48 hours, were given basically the data at the beginning of 48 hours, and then were told, go forth and train these systems in identifying these gliomas in these MR brain scans. And they were able to use our systems that weekend. We gave them sort of unvetted access to be able to go to the front of the queues for that weekend. But they were able to go through and, using the 3 different systems that we have, train these models in less than 4 hours. So they came in way ahead of the game with the data that was provided. And the accuracy of what they had in the models that they've developed over the years is hitting nearly the 90% accuracy level, which is mimicking sort of what a human radiologist can do. So these are some of the capabilities that we have that are affecting sort of real-world, forward-looking things. We do other things. We do a lot of genomic work, whether it's genomic work with some of the cancer work at MD Anderson, but in this case, this was analyzing genomes of anthropological samples across Europe, where they were trying to understand how the 3 different branches of people started coming into Europe to understand the historic makeup of the European continent. It was an interesting result that actually led to a surprise that there were these 3 that came in very distinctly at different times, and led to sort of the cover of Nature, which was a pretty cool result. And then the other one this is just sort of, because I wanted to brag on this a little bit, this is the second one I've actually been involved in, but LIGO won a Nobel Prize for its gravitational wave detection, and TACC played some part in this. Not just in that we had 7 million processor hours that they worked with to recompute all of their data, but we actually worked very closely with them as they were doing this and helped them to re-optimize their workflow to get a factor of 3 more performance in their workflow, which basically turned that 7 million processor hours into 21 million processor hours, plus all the other systems that they worked at around the world. So these are some of the things that TACC does working with people, is help them optimize and make their workflows go better. This is one example from the Wrangler system that we have. I'm doing good on time. The Wrangler system is this flash-enabled small cluster. It only has about 100 nodes. But it's meant for doing high-speed I/O. And so there's a very large project, which, as you can tell by the scale of it being on the continent of Australia and all the way out to New Zealand, it's a radio telescope that's been proposed for 2024 called the Square Kilometre Array. And in order for them to be able to do their job, they need to get up to the level of ingesting a petabyte of data a day, which seemed 10 years ago when they pitched this like it was something that wasn't going to be very easily achieved. It just, that wasn't coming. They came to us and talked to us and said, can we try it out on this Wrangler system? And they got to 7 gigabytes a second without even trying. And in fact, when they went through and benchmarked this, they found out that the problem was that they were using Java, and Java's I/O is just too slow to do what they need. So they just need to rewrite all this in a faster language. So Wrangler has been used in many other sort of aspects of this. In fact, Chris Mattman has a deep and dark web project that he's been working on, going through more nefarious corners of the web and getting information, identifying information about everything from arms trafficking and other sort of nefarious bad things, but understanding how to bring all that information together and make it into an actionable product. You guys have traffic here in Houston too. We have it in Austin. Austin seems to be new to the game, so we're still learning. But we've been working with the Center of Austin and the Center for Transportation Research to take some of the video off the poles coming in from the different intersections around town. And using machine learning and image identification, you can see here going through, it's identifying cars in this case, and the person standing there. And so it's actually identifying different entities, from buses to cars to people to cyclists, You can actually see that lamppost keeps lighting up over there because it keeps thinking it's a person as the wind moves the image around on the, or moves the pole around so the image moves. But it's creating an indexable and searchable three-dimensional model of the intersection, so that not only can you do sort of simple car counts, which people have been doing for a while, but you can then start talking about this person's about to get on a bus, or this person went out into the intersection and had a near miss, which is not something that we normally get reported. So we don't know the almosts at a lot of the dangerous intersections. And so this is something that we really want to sort of push forward to promote a safer environment around cities, as well as all of the connected car and IoT things that go along with this. So some very, very interesting stuff around that. So that's sort of the technology stuff that we do. And all that's great. And we've got a lot of people here who have been talking about algorithms and ways to make all this work. But as I think we all know, in modeling and simulation 10 years ago, it was all about big iron. And we've moved into an environment now where there are only so many people that can write HPC applications. And we're sort of at the same point right now with data. There are only so many people that know how to truly train a data model, the data set, and then evaluate how it's working and getting it out to people. So a lot of what we do now is developing these high-level interfaces for people. And so these three down at the bottom are three of our bigger ones that we're working with. I'll talk about one in just a second. But we've gone from 5 years ago where we had almost no web presence. We had a web page. Everybody's got a web page. To now we have more people who are doing active web development to build these portals and front ends and the supporting back-end infrastructures so that we can let people forget about the big iron and focus more on the research that they need to do. One example of this is DesignSafe, which is building up an entire web front end to allow civil engineers to explore natural disaster. Seems disaster keeps coming up, but this is an area where people who can bring in from shake tables and large labs around the country all sorts of data, and other civil engineer researchers can come in and they can launch these jobs on our large systems, not even knowing really what they're doing. They say, I have these data sets, I need to run OpenCs on it, it's going to take this much memory to get this through. And it really is sort of a point and click environment. Or if they want to, they can even dive into Jupyter Notebooks so that they can write all this down, comment it all up, and do the visualizations, which are really what they need to take away from this to understand what's going on. Once they've done that, they can then publish and share those results for other people. So it gives that full reuse of the data as well as what they did. So it's a really interesting project in its second year now that we're going to push forward based on many of the other technologies that we've used all around. They're going to have a few petabytes of data by the time they're done, but we support probably somewhere between 100 to 200 different data collections at different levels. And really all data is big data to someone. And so we have different web portals that allow people to do the analysis that they need to on all these different data sets from over there on the, let's see, am I doing right? Yes, on that side of the screen, there's the herbivores and fishes of Texas. So if you're interested in where to go fishing, we actually have a good map of where all the different fish are around the state. You have digital rocks here in the middle, which is studying the porous nature of rocks and cataloging all of that. Aeroport is a very important site for understanding the genomic nature of one particular kind of, it's a mustard plant, isn't it, Joe? I'm not a biologist, so I have to ask one of ours. But it's a fundamental plant because it's the reference genome against which most plants are judged. And then lastly, PaleoCore is putting together paleontological studies from around the world across time so that we can really start to understand not just what individual digs were, but help people to merge all of this data into one place, which is a common theme in all of this, is how to bring these large silos of data together into a collection that's usable by a researcher. So TACC as a whole sort of provides what we think of as two different sides of solving the problems of that in-between in research today. We have large-scale systems, many different kinds that cover different aspects of the problem. And then we have many different people who have understandings working in visualization, web interfaces, and data services, but then also do a lot of that sort of embedded collaborative data science that you were talking about. And that's where a lot of what our work is done, is in that collaborative, working with somebody from the city of Austin to figure out how to apply image machine learning. We work with a lot of different people, so I decided to make some NASCAR slides here, as I call them. So we are part of the University of Texas system, but we actually do work with all the other public university systems, and hopefully, we work with Rice as well. So we're friends. But they're the folks who have come in and bought into some of our systems. We're accessible through Exceed, which is the National Science Foundation's open science research platform. Most of our systems, I think about 60% of our funding comes in from the National Science Foundation, and our larger systems, that's the way most of the allocations are made, although UT holds on to 10% of all those systems, so we can do other things with them. But we also have, outside of that academic environment, we really are interested in making the world a better place, and part of that's academic, and then part of that is also going out into sort of the working with industries. And so we have this program that we call the STAR program, which is our industrial affiliates program. And I know there are several folks here from BP and other places. You'll see here there are a lot of various technology companies that are coming in. We work very closely with them to understand what they're doing and to help them understand what the other side needs. As well as, Firefly Systems is building rocket ships in Leander, Texas, just out of Austin. They're building a new style of engine to launch microcube satellites. And so we have people that join in to use some of our systems. In fact, they came to Austin because they knew they could use the Stampede systems for their CFD computations. We do a lot of training with folks from these companies as well. We host various how to use Pythons, a lot of the getting started stuff that might not be as interesting to people here. But then we also have week-long trainings and everything from, deeper dives into how you can do, running machine learning, training machine learning applications to do the thing, to, we actually have one where we teach everybody how to run systems the way that we run systems. And that people find is a very important thing to share, so that this is what we spend all of our time doing. If we can share that with you guys so that you can make your companies work better, everybody's a winner. So that's sort of what TACC is, what we do. We like to say that we are not just working to exascale, we're going to Texascale because we're proud Texans. But this means continuing to make bigger, faster pipes, faster computers, and make them work well in a variety of applications, but then making these powerful user application interfaces so that people can actually take advantage of using, say, 10,000 cores on a supercomputer at the push of a button, which they can do. And so this will allow the impact of the systems to reach a much broader audience, but then also not just making generic interfaces that people can use, but making these interfaces so that everybody can actually run their applications and have answers given to them in ways that they're familiar with. So giving individual communities that which they need. So that's sort of an introduction to TACC and what we do, or some of the things we do. I know I left some things out, but open it up for questions.
Yep. And we do have time for some questions, so if you have some questions. So we have one back there.
So I wasn't clear if you mentioned that. What are the projects you kind of work with on with the open source community? Have there been some things that you guys committed to open source?
We have many things. I mean, HPC Wire just ran something that our two-factor authentication is an open source product that everybody can now come and run for their systems. We have many people. All of the software that we develop at TACC is open sourced. And so that's the easiest answer. But more than that, we actually do work very closely with Intel to make sure that their software gets right, or that what they're doing is contributed back into the open source project. So all of that cafe stuff I was showing is back in the system after having worked through all this.
So one of the things here, maybe you can speak a little bit more to, and I'm going to ask the question while the microphone gets passed around. how do you engage with TACC? Because your mission is at some level to support NSF and NSF agencies, and and we as academics are that. But there's a lot of non-NSF academics in the audience here.
That's what I was trying to pitch on there. I notice I only said NSF twice.
Yeah.
Well, we are trying. I'll say first and foremost, we're trying to diversify, because in this day and age, much like your 401k, you want to diversify. But interacting with TACC is usually, it can start off with, I can hand you a business card, you can drop me an email, give me a call, I can put you in touch with Melissa if we're doing STAR affiliate things to talk about how we can just get together and get started to take advantage of some of the knowledge or the systems that we have. For researchers, there are, you can go through the NSF ways, but there are also ways that we do a lot of sort of cost recovery. In research, people don't like, especially in the data realm, to have to go every year and get an allocation on a system. And so we actually can cell cycle, cell storage at rates that are affordable to academics, I think is probably the best way to put it, but reliable. And so, we're talking less than $100 a terabyte per year for replicated long-term online storage. Hard to beat. But those are the sort of things that we can do to help researchers on both the academic and on the enterprise side.
Any other questions for Niall? Are you going to be around, by the way?
Yeah, I'll be around.
Okay.
I'll be around until at least about 4 or so.
Okay. So any other questions?
Got to try and beat I-10 though.
If not, join me in thanking Niall again. So yeah, thank you.